Alright, so last thing we want to look at in this first unit on quadratics is just trying to put everything together and do some word problems with them. But before I get into that, there's just a little warm-up here on the screen just to try and remind yourself from the last few lessons. So give this a try and push play when you're ready to go through it together. Okay, so first thing you want to look at here, when A is asking if the relation has a maximum or minimum, remember that to find this out, what it's really asking is if the parabola opens up or opens down. So if our parabola opens down, like we see here, we're actually going to have a maximum, but if we open up, we're going to have a minimum. Okay? And you're used to finding whether or not it's a maximum or minimum by looking at the a value of the equation. That's from standard form. Now, unfortunately, here we're not in standard form, and a common trap that people fall into is they look at the a value they have in factored form, and they look at this and say, oh, here there's this would be a 1, so it's positive, therefore I'm opening up, and it's a minimum. And they seem very happy with that, but it actually turns out to be incorrect, because if you actually look at the graph over here on Desmos, we can see that the parabola opens down, so we actually do in fact have a maximum. So how can we sort of negotiate around this? Well, yeah, remember, you're looking at the a value from standard form to help you determine whether it's opening up or down. So if you want to be completely sure, you got to look at standard form. So if you were to expand this one out using an array, okay, so you give yourself x minus 5 and 3 minus 2x. Okay, you would wind up with minus 2x squared, 3x, minus 15, and then another 10x here. So you'd actually wind up with, in standard form, negative 2x squared plus 13x minus 15. So once you have in standard form, you can very, very clearly see that our a value here is negative, and since it's negative, it tells us we're opening down, so we have a maximum. Okay, and if this seems like a lot of work to do, it might seem like a lot of work just to find out one little piece of information, but if you're just trying to find out if it opens up or down, you don't need to do the entire standard form. All you're really concerned about is the coefficient of x squared, because that's what gives you the a value. So in your array, once you fill this out right here, just if you're looking at your x terms, you have minus 2x here, you have x here, you have 1 out in front, so right away you might be able to see that I'm going to get negative 2x squared plus whatever else. And all that really matters there is that a value being negative. So just be careful with that trap. If they give you the equation in factored form, don't just assume that the a value in front tells you the direction of opening. You gotta look at the a value from standard form. Okay, with that in mind, let's take a look at our zeros. So remember, to get our zeros, we take each of our factors, set them equal to 0, and solve for x. So our first factor is x minus 5. Set that equal to 0 and solve for x. Our second factor is 3 minus 2x. Same deal, set equal to 0, solve for x. So in that case, we get x equals 5. And from here, we wind up with, after some algebra, we get x equals 3 over 2. Okay, so those would be my two zeros, or my two x-intercepts. Okay, and I'll be able to see those if I look at my graph over here. So x equals 5, and x equals 3 over 2, or 1.5. Okay, to find our axis of symmetry, again, if we look at our graph, we can see it very plainly. It's going to be the x value that cuts the parabola in half, so it's going to be at 3.25 here, but again, we always have the graph handy, so you got to be able to calculate that. So again, to find our axis of symmetry, we're going to take our two zeros, average them, so add them together and divide by 2. So our axis of symmetry will be x 5 plus 3 over 2, all divided by 2. Okay, so you do some quick work with the fractions here. This gives you 5 is 10 over 2, so 10 over 2 plus 3 over 2 is 13 over 2. So you get 13 over 2, all divided by 2, which is 13 over 4. Okay, and now to find the optimal value, again, if you look at our graph here, the optimal value is the highest value the graph reaches. So from the graph, we can see it's at 6.125, but to calculate that, remember that it's part of our vertex, is the y value of the vertex. So if we have the x value being 3.25, or 13 over 4, we can sub that in the equation for x to find our y value. Okay, so we're going to take our equation. Again, you can I have standard form here, and I could use that if I wanted to, but I'm going to stick with the factor form I was given to start with. So I'm going to take y equals my x minus 5, my 3 minus 2x, and every x I see gets replaced with 13 over 4. Okay, and at this point, it just becomes simplification. Okay, so let you guys work through that one. 13 over 4 minus 5 gives you negative 7 over 4. The second factor bracket simplifies to negative 7 over 2. So you wind up getting a y value of, looks like 49 over 8. Okay, so again, the vertex is an x value of 13 over 4 and a y value of 49 over 8, but if you're just looking for the optimal value, all you care about is the y value, so it's 49 over 8. Okay, so with that warm-up finished, let's try an actual word problem now. Okay, so take a minute to read through this one. We've got a company manufacturing snowboards. You have a relation here to model its profit. So in the model, x represents the number of snowboards in thousands, and p represents the profit in thousands. So quick little fix here, this y value should be a p. Okay, so you have p equals negative 81x, bracket x minus 2. So one of the things with word problems is, we're now at the point where, given an equation in factored form, we can find out lots of different information. We can find the zeros or the x-intercepts, the axis symmetry, the optimal value. You can find the y-intercept as well. And with word problems, that's really what all you're going to be asked to do is find different pieces of that parabola, but part of it's getting around the language and is trying to figure out what part of the parabola we're trying to find. So part A asks for the maximum profit the company can earn. Now, in terms of for which part of the parabola you're looking for, whenever you see the word maximum or minimum or highest or lowest or most or least or anything along those lines, that suggests an extreme value, so the word vertex should be jumping out at you. So when you see the word maximum in this case, you should know you're trying to find something to do with the vertex. Now, okay, so the vertex can have two parts, an x value and, in this case, a p value, or dependent variable. Now, what's it actually asking for? Well, it's asking for the profit in this case. The profit is the dependent variable in this case, normally our y value, in this case p. So the y value of the vertex is the optimal value. So really this equation is just asking us to find the optimal value of the parabola we have. Okay, so again, to help us with the visual here, we can always take a look at the graph by plugging into Desmos. So here's our graph. So I have y equals negative 81x bracket x minus 2. Here's what it looks like. So again, remember here x represents the number of snowboards, and it's in thousands. So that's along our x here, and y, or a p-value in thousands, is our profit along the y value. So we can see our optimal value here. It's in the vertex, the y value is 81. So we can see our profit is going to be 81,000. But how are we going to calculate that? So remember, it's going to be halfway between our x-intercepts to find the axis symmetry, and then from the axis symmetry we can find our optimal value. So remember here, if you look at our equation, we are in factored form. Okay, and this might be a bit confusing because it doesn't necessarily look like it's factored form, especially because you only see one bracket, but it's actually is factored form, because if I think about it, if I were to give you the equation p equals negative 81 x minus 0 x minus 2, you probably look at that and undoubtedly say, okay, that's factored form. Now I see the two brackets. But however, x minus 0 subtracting 0 doesn't change anything. So this simplifies to just negative 81 times x minus 2, which makes, and that first set of brackets around the x is redundant, so it just simplifies a negative 81x x minus 2 without the brackets around the x. So this actually is factored form, even if it doesn't look like it. So our factors here are going to be x and x minus 2. So our zeros are going to come from when x equals 0, which is clearly when x equals 0, or when x minus 2 equals 0, which happens when x equals 2. Okay, so there are two zeros. Okay, remember with our two zeros, you can find the axis symmetry just like we did in the last equation. So our axis symmetry is going to be 0 plus 2 all divided by 2, which is going to be 1. Okay, and then again, so this would give us the x value of the vertex, so that would be the number of snowboards that gives you the maximum profit, but we're actually looking for the maximum profit, the optimal value. So we're going to do that over here and put that x value of 1 into the equation for x. So I'm going to have p equals negative 81, x becomes 1 in each of these cases, so I have 1 times 1 minus 2. So I simplify that, I get negative 81 times 1 times minus 1, so I get 81. Okay, so p equals 81, that's our maximum profit. We did say the profit was in thousands, so that should tell me overall that my overall maximum profit is going to be $81,000. Okay, and again, I could see that from my graph just by looking at the optimal value. Okay, right there. for B, it asks how many snowboards we have to produce to earn that profit. So again, if you think about this, the profit that we're trying to earn here is the maximum profit, the 81,000 that we just found. How many snowboards will it take? Well, we actually already found that out, because looking at our graph, it's going to be an x value of 1 that gives you that maximum profit. So the feature of the graph we're looking for is actually going to be our axis symmetry, which we already found. Okay, so this one becomes relatively quick. We know our axis symmetry is at x equals 1, so it'll take 1,000 snowboards to maximize that profit. Okay, and again, it's just asking for different features of the graph. So here it asks for the number of snowboards, which is an x value, to produce the maximum profit. So the x value of the maximum profit is the axis symmetry, which was x equals 1. Okay, and last but not least for this one, a term that pops up often in business talking about profit is what we call the break-even points. So when you're breaking even, you're not gaining money, you're not losing money, so your profit is actually 0. So where's profit actually 0? Well, again, let's take a look at our graph. Well, our profit is 0 at the x-intercepts. So it's going to happen twice here. We can see it's going to be at 0 and 2. Those are the features of the graph we're looking for. Again, these are things we've already found. Okay, we're in factored form. We get our zeros. Our zeros are going to be at 0 and 2. So that gives the answer to this guy. So the company will break even if they sell no snowboards or if they sell 2,000 snowboards. All right. One final example. Alright, so once you take a minute to read through this one, so in this store, this woman Shirley sells some t-shirts for $10, and right now when she sells those t-shirts, she sells 45 of them a week for those $10. And she wants to try and earn more money, and so she's done some research that tells her that she can increase the price by $2 on the shirt if she wants, but that every time she does that, sales will go down. People won't want to pay the higher prices, so she'll sell 3 fewer t-shirts per week. Okay, so again, she'd want to change the price to try and earn more revenue, but again, there's going to be some sort of point where she's going to increase the price so much that nobody's going to buy the shirt. So she's trying to sort of maximize her revenue. So before we get into how she can maximize her revenue, right now, if she wants to, if she sells those 45 t-shirts at $10, well, how much revenue does she take in? So one thing to remember about revenue, it is equal to the number of items sold times the price you're selling them for. So in this case, she's selling the 45 t-shirts for $10 each. So 45 shirts times $10 gives you revenue of $450. Okay. So now we're going to see what happens if she tries to change the price. So if she changes the price, so right now she doesn't change the price at all. She's selling them for $10. Okay, so 0 increase to $2. So $10 for the price of the shirt. She sells 45 shirts, which gives her a revenue of $450. So what's going to happen each time she changes the price? Well, if we change the number of increases here, then her price starts at $10, but now she has one increase of $2. Okay, so you can probably think to yourself, okay, if she's increasing the price once by $2, those are now selling for $12. Okay, so now her new price is $12. Well, how many shirts does she sell now? Well, we were told again that every time she increases the price, she sells 3 fewer shirts. So the number of shirts she sells will be 45. And she's had one price increase right here. She's going to subtract 3 from her sales once. So she subtracts 3 from her sales, and now she sells 42 t-shirts. Okay, so her revenue, again, price times number sold is going to be 12 times 42. Which you can work out to be $504. Okay, so I'd like you to, we're going to continue this in the next video, in part 2 of this lesson, but I want you to just try and finish up this table here. Go up to 4 price increases, so see what happens to the price every single time it goes up, what happens to sales every time it goes up, and what happens to the revenue. And then try and create, if we were to instead of trying to guess the number of price changes as 1, 2, 3, 4, 5, 6, whatever, we just let that number of price changes be X, what would our price, number of t-shirts, and revenue look like? Okay, so we'll pick this up in part 2. See you over there.